All right, so we have proven of the special case of the inverse function theorem, we have proven part 2 here. Now we're going to focus on part 1. So we're going to prove that the image of U, which remember we made U here be a ball centered at A, with the property that... I just noticed a mistake from the last video. With the property that f prime of x should be within 1/2 of the identity. So this was our U, and our goal now is to prove that the image of U, which we can call V, is an open set. So that's what we'll try to do in this video. All right. So in order to do this, we will need some of the tools we set up in the previous video. So we will need these phi sub y's. These are going to be useful basically throughout this entire proof. So remember the definition of phi sub y, that's here. And we'll also need this fact about phi sub y here that we got using theorem 9.19. So we will need to remember that. That phi sub y is a contraction. It's almost the sort of thing we can apply the contraction mapping theorem to, except right now we can't because we do not know that phi maps U into itself, and also U is not even a complete metric space. So our goal as we work to proving number 1 here, our goal is actually going to be to apply the contraction mapping theorem, which we have not done yet. So we will have to restrict to a smaller set, smaller than U, which has the property that as a metric space it is complete, and also which phi sub y definitely maps into itself for some y. That's the situation that we're going to put ourselves in. I haven't brought in a y yet, so that probably doesn't make sense, but let's just start with the proof of 1. So proof of 1. Now, the goal, so remember we defined V to be f of U, where U was that set described above, that ball of radius delta. Then in 1, we want to prove that V is open. So let's fix some y naught in V. So fix y naught in V. To prove V is open, we must prove that there is some radius that's small enough so that a ball of that radius centered at y naught is fully inside V. Now let's draw a picture of what is going on so far. So right now we've got our domain E, which is this big set, subset of Rn, and we've got F maps E into whatever is the image of E, also some subset of Rn. And there's this point, so there's a set U, which, it doesn't look like that. It actually literally looks like a ball, right? So there's a set U that looks like that. The center is A. And somewhere over here, there's f of A. And there's a set V, and I don't know what V looks like. It's the image of U. So the definition of V is the image of U. And right now we know that f restricted to U is injective. So, I mean, that's what we proved in the last video, right? That was number 2, fact number 2. So f is a bijection from this set onto this set, from U onto V. And we have picked some random y naught in V. Let me use a different color. So we picked some random y naught in V. F is a bijection from U onto V. So there's 1 and exactly 1, let's call it x naught, such that f of x naught is y naught. So define, and that x naught has a name, right? F restricted to U is invertible, so it has an inverse, and I can apply that inverse to y naught. So just define that to be x naught. So that just makes it so that f of x naught is y naught. Now, okay, so x naught is a preimage for y naught, right? Remember how that family of functions phi gives us a way of talking about when points are preimages of other points? X naught is a preimage of y naught. That's the same as saying that x naught is a fixed point for phi sub y naught. So phi sub y naught, that's going to be a map. Let's see, how do I put that into the picture? So I'd like to view it as a map kind of from, well, okay, so phi sub y naught, I'm thinking of x naught as a fixed point for phi sub y naught. So I want to think of it as a map from this space kind of back into this space. So maybe something like this. Although that looks like it's suggesting that phi sub y naught maps u into itself, but I don't know that that's true. So maybe I should not do that. Okay, so just think that phi sub y naught maps this space into itself. And let me write down this fact. Since x naught is a preimage for y naught under f, phi sub y naught has x naught as a fixed point. And phi sub y naught is a map from this space here into itself. So from E to Rn. And what we're going to do, so phi sub y naught fixes this green point here. So it sends the green point to the green point. And other points, it might move them around. So what we're going to do, let me zoom in here on the picture here. So this green dot x naught here, this is a fixed point for phi sub y naught. What we're going to do is come up with a ball like this, centered at x naught. And we're going to make the ball small enough that we will see that phi sub y naught will end up being a map from this ball into itself. So that's what we're going to do. And we're going to make it a closed ball, meaning we'll include the boundary. So we want to arrange it so that we have a closed ball here centered at x naught, including the boundary, so that it's a compact set, which makes it a complete metric space. And we're going to arrange it so that phi sub y naught maps this ball into itself. Then we can apply the contraction mapping theorem, which will help us here. I'm sorry, I just paused the recording and came back because I realized that what I said was not so helpful, actually. If you just know that, applying the contraction mapping theorem to phi sub y naught is not so helpful because x naught is a fixed point for phi sub y naught. So we already know it has a fixed point, and the unique fixed point is x naught. That's actually totally useless. We're going to arrange it so that when you put in phi sub y here, where y is going to be one of the points over here. So y is going to be a point that's pretty close to y naught, and we'll say exactly how close in a moment. So y will be some point pretty close to y naught. And we're going to apply the contraction mapping theorem to phi sub y. But to get this to work, we're going to need to make a ball centered at x naught that is small enough that even its closure is inside u. Okay, so let's see how this pans out. So yeah, this thing that I wrote in red is true, but I don't know actually how helpful that is. Okay, let me just go ahead and put things back into perspective. We're trying to show that the set V is open. We're trying to show this set is open, so we have fixed y naught. And that means we're trying to find a ball centered at y naught that's fully inside of V. That is the goal. And we're starting by first looking at the unique preimage for y naught, which is x naught over here. And then we're going to just let this red ball here be any ball whose closure lives inside U. So choose R greater than 0 such that BR x naught, the ball of radius r at x naught, is fully inside of U. This is something we can definitely do because U is open and x naught is in U. Right? X naught is in U because it's the preimage of y naught, and y naught is in V, and F maps U bijectively to V. So this we can do because U is open. U is known to be open. Okay, but this is not good enough. I actually want the closure of this thing to be inside U. And that means I might need a smaller radius. So actually let me call this here R naught. And then let's let R be half of R naught. Then, not only is the ball of radius R inside U, but so is its closure. Its closure is also inside U. So R will be the radius here. This distance will be R. And let's call this set B. B will be the closure of the ball of radius R centered at x naught. So B is the set in red here. Is the disk here in red. Now, here's what we're going to show. And this will achieve the ultimate goal of showing that V is open. So we will show that if you take a ball of radius 1/2 centered at y naught, that means over here, take a ball of radius 1/2, then we're going to show that that is fully inside of V. And according to the definition of open, that's what we need to show that V is open. We fix arbitrary y naught, and then we need to find a radius small enough so that a ball of that radius is fully inside of V. Sorry, not 1/2. 1/2 R. 1/2 R, where R was the radius we got here. Half the radius so that the ball of radius, yeah. So this would be a quarter R naught. Okay, so we have to prove this inclusion, so let's fix y in there. So I'm making y yellow so I can add it to the picture. So fix y in there, and then we'll try to show that y is in V. Want to show y is in V. Okay, so this y is some point that we fixed, some yellow point that we fixed in here. And this picture is already biased because the picture is assuming that this red disk is inside of V. But that's actually what we're trying to prove, right? So our goal is to prove that y here is inside of V. Okay, so looking at this picture, you might be tempted to say, well, this yellow dot y over here has a unique preimage back here in U. But again, the picture is biased. We're trying to prove that the yellow dot y is in V. We're trying to prove that this red disk is fully contained in V. So as far as we know right now, we have to assume that y might be outside of V. So there might not be a unique preimage for y. In fact, we don't even know that there is a preimage for y at all. Okay, so pretend that we don't know whether this yellow dot is inside V or not, and so we don't know whether there even is a preimage. And previously, I think I prematurely started introducing this phi sub y, but now there's something called phi sub y. It's phi sub this yellow y over here. So that's the function we're going to focus on. And remember that its fixed points are going to be preimages for y. The fixed points of phi sub y are going to be preimages under the function f for y. So there will be things that map to y. So if we can find a fixed point for phi sub y, that would be really good. Because then we'd have a yellow dot over here that gets mapped to the, I guess I should point that way, that gets mapped over there to the yellow dot over there. And that would tell you that the yellow dot over there is in V, right? Because if it's the image of something in U, then it's in V. That's the definition of V. It's the image under F of U. So that's the plan, is to try to find a fixed point for phi sub y using the contraction mapping theorem. So again, to apply the contraction mapping theorem to a function, it has to be from a metric space to itself, and the metric space has to be complete, and the mapping has to be a contraction. So all we know about phi sub y is that it is a contraction, but, I mean, if you call this condition the condition of being a contraction, but we don't know that it maps a certain complete metric space to itself. We hope that that complete metric space will be B here. So first let's observe that B is a complete metric space. So B, well, B is the closure of a ball, right? So that means it's bounded. You know, it can be fit inside a larger ball. It is a bounded set, and it's the closure of something. So it is also closed. So B is closed and bounded. By the Heine-Borel theorem, B is compact, because we're talking about subsets of Rn here. So B is compact because B is closed and bounded. So this is by the Heine-Borel theorem. That means B is complete. So as a metric space, B is complete. We worked hard in the last quarter, if you were in my 118b, we worked hard to prove that compact metric spaces are always complete. Then we can apply the contraction mapping theorem. So remember how that was important? When we proved the contraction mapping theorem, we had to, we defined a certain sequence, showed it was Cauchy, then we had to use the fact that it therefore converges. So this completeness was crucial. Okay, so then if we show that phi sub y, where the y is the yellow y that I fixed here, fixes B as a set, so maps B into B. Sorry, I shouldn't say fixes B, just maps B into itself. If we show that, then we can apply the contraction mapping theorem. let me just write CMT, contraction mapping theorem, specifically to phi sub y restricted to b. And that would get us a fixed point. And that's really useful because that would be a preimage for y. And that's exactly what we need to prove that the yellow y is in the set V here. Okay, so to prove this statement here, let's fix here, let's say consider any old x in B. Then we must show that phi sub y of x is in B. That's how we prove this statement that I boxed in here, right? So any x in B, and we must show this. So in the picture, you should think that x, this x that I'm considering, is just anything in this red disk here. So I'm considering an arbitrary x in the red disk here, and I'm trying to show that phi sub y of x is also in the red disk. So I'm trying to show that what I'm indicating by this arrow is really honestly true, that phi sub y does map this set into itself. So to show that phi sub y of x is in B, well, I should look at the definition of B. It's a ball of radius r centered at x naught. So I need to look at phi sub y of x, the distance from x naught. And I hope that this is less than r, or less than or equal to r would be okay, since this is a closed ball here. Okay. So let's analyze this. So to do this, we're going to bring in a middleman and use the triangle inequality. So we'll look at phi sub y on x minus phi sub y on x naught. That'll be the middleman. Phi sub y on x naught. And here let's compute what is phi sub y on x naught, or rather let's compute this term. So let's compute this on the side separately here. So this term is, so phi sub y, that was, okay, I don't remember exactly. It was this, y minus fx naught plus x naught. And then I'm subtracting x naught, and I get y minus fx naught. Okay, so the reason for introducing this middleman, phi sub y of x naught, into the inequality is so that we can use the closeness of y to f of x naught. In other words, the closeness of y to y naught, right? The yellow dot over here is within 1/2 r of the green dot down there. Okay, so filling in what I just got here, sorry, just trying to put everything into view here. So over here we got y minus f of x naught, which f of x naught is y naught. So let me just write it that way, y minus y naught. And then over here I'll just leave this as is. Now, remember this property that phi sub y has. Since, thanks to the way that u is chosen, remember at the very beginning we chose u so that the derivative of f never strays too far away from the identity. thanks to that, we were able to apply theorem 9.19, and we got a nice bound. Well, thanks to that, we got a nice bound on the derivative of these phi's, and thanks to that, we were able to apply theorem 9.19 and get this inequality here, this contraction kind of property. This is anytime x1 and x2 are in U, we get this inequality. So going back down here, x and x0 are points in U, right? Because x here is in B, and B is a subset of U, right? That's the way this red disk was chosen, is so that it's a subset of U. And x0 is in U. I mean, x0 is also in B, and B is a subset of U. Yeah, we also knew from the very beginning that x0 is in U, since it's the preimage of something that was in V, namely y0. Yeah, so x and x0 are in U, so that inequality holds. And so here we get less than or equal to 1/2, and then the distance between x minus x0. This is that contraction property for phi sub y. And the distance between x and x0, well, x is in this red disk of radius r centered at x0. So we can put r here. And I'm putting less than or equal to because I know only that x is in the closure of that disk, not necessarily that it's in the interior. And the distance between y and y0, well, look where y came from. Y is within 1/2 r of y0. So now you know why 1/2 r was used there. And actually, this is now a strict inequality, since this is actually strictly less than 1/2 r. Not that it needed to be, but it just is. Okay, great. So phi sub y maps x to something that is within distance r from x0. So phi sub y maps x into the set B. And so we have proven this boxed-in statement here. Phi sub y maps B into itself. Okay, now we can apply the contraction mapping theorem. By the contraction mapping theorem, phi sub y has a fixed point. And now we're very excited because we have just worked hard and applied a powerful theorem. Let's call the fixed point. Oh, so not just phi sub y restricted to B, right? We're using the completeness of the metric space B. So let's call the fixed point x, which is a point in B. Okay, don't confuse this x with the x up here. The x up here was just for the purpose of proving this boxed-in thing, right? This consider any x in B, and then we blah, blah, blah. This is done. So this was its own little self-contained proof of this statement here. And it is done. Okay, so right now there are no x's. Let's call our fixed point for phi sub y, let's call that x. X is a great name because f of x is y. So since phi sub y maps x to x, remember the way these phi sub y's work? When you have a fixed point for phi sub y, that's the same as having a preimage for y. So we have f of x is y. Okay, but x is in B. So x is in U. Remember, B is a subset of U. So y, which is f of x, is in f of U, which is by definition V. So y is in V. And this is what we needed to prove. So going back to the picture over here, let me summarize the argument. The way this started was we picked a disk of small enough radius that its closure is inside U. Then we went over here to y0, and we picked a disk centered there of half the previous radius that we got over there. Then we picked an arbitrary y in that disk, and then we tried to show that y is in V. And the way we show that is by looking at the mapping phi sub y and showing that it maps this closed disk into itself. Then we can apply the contraction mapping theorem to phi sub y, which tells us that there's a fixed point. So there's some yellow dot in here, which we decided to call x, such that phi sub y maps x to x. Now, since x is in the red disk, and the red disk is a subset of this white disk, x is in the white disk. So x is in U. And since x is a fixed point of phi sub y, that makes x a preimage for y, meaning the yellow x goes to the yellow y. And the definition of V over here is that it's the image of U. It's whatever is the image of U. So since the yellow x is in U, f of the yellow x must be in V. In other words, the yellow y must be in V. Okay, so let's just go write our victory sentence down there. Thus, V is open. And we have proven part 1 of the theorem. So here is where we are now. This is our inverse function theorem special case. We have proven part 1, and we have proven part 2. We proved part 2 in the last video, and we just finished proving part 1. So now we know that getting away from the special case, going back to the original inverse function theorem, now we know that if you have a C1 function which is invertible at whose derivative is an invertible linear map at a certain point A, then we know that there's a neighborhood of A on which f itself is invertible. The original function is invertible. And the image of that neighborhood is going to be another open set. So if you take the inverse of f, it'll be a function from an open set to an open set, a bijection. And it remains to verify, so that'll be in the next video, that when you look at the inverse, going the other way, that's actually differentiable. And we will not only verify, we'll say what the derivative is, although you can probably make a guess.